Welcome. In this lesson we begin Chapter 4, Applications of the Derivative. In Chapter 3 we learned how to take the derivative of all different kinds of functions, and now we turn our attention to applications. What can I do with the derivative? In 4.1 we begin Maxima and Minima, understanding ideas about the high points and low points of a function. Where does a function reach its highest value? At what value of x does a function reach its lowest value? We'll talk about two different kinds of maxes and mins, absolute max and min, local max and min. And then we'll look at the idea of a critical point, and then we'll use critical points to find absolute extrema on a closed interval. All right, let's begin. The highest and lowest function values are the absolute max and min. When I say function values, I really mean vertical components. In the picture to the right, f of p is greater than f of r. So what does that mean? I look at my p, I go up, and so this height, that's my f of p. That's just a little bit higher than f of r. So if I go to r, the top of that hill, and it says that f of r is equal to f of b. So at the very right side I go up. If I were to take that across. So on the interval from a to b, this is a closed interval. It contains its left endpoint and it contains its right endpoint. On the closed interval from a to b, function f has an absolute max at what x equals, looks like p. X equals p, and an absolute min at x equals, let's see, what is the lowest value? It looks like when my x value is a, that's when the function has its lowest point, so a. Now what about if I restrict my attention to the interval from q to t? This closed interval from q to t. F has an absolute max, well, let's see, not q, maybe r. Is r the point? Maybe r. And an absolute min, let's see, the lowest it gets right there at s. X equals s. When we talk about maxes and mins, we're often concerned with the x value where these maxes and mins occur. What is the x value? Not necessarily what is the actual maximum value or the actual minimum value. But now we've identified some x values, let's turn our attention to the actual function value. How about this first one? The greatest value that f actually attains is f of p. So f of p is a y value. And how about the last question here, the lowest value that f attains? Well, it's going to be right down there. We'll call that f of a. Now we look at a second kind of max and min, a local max and min. So look at things like these areas that I've circled. Two of those are minimums. They're not the lowest min in the entire graph, but it's kind of a min in its local neighborhood. Same thing around the s. When I look at x values around the s, then the smallest function value happens right at x equals s. So that's the idea of a local min. Let's identify the actual x values where these local maxes and mins occur. So how about a local max? Let's see, 1, 2, looks like I have two local maxes. So x equals p and x equals r. X equals p, x equals r. Oh, why don't I include the endpoint here, b? B is not where a local max occurs. In order to be local, the function has to be defined around that x value. But for b, the function is not defined to the right of b. If I try to plug in x values that are bigger than b, I don't have any curve there. The function just isn't defined. How about then a local min? Do you see where the local mins are? There, but not the endpoint, not a. So it looks like maybe q and s. X equals q and x equals s. Officially, here's our definition. Officially, function f has a local max at x equals c if two things. First, f is defined at and around c, and if f of c is greater than or equal to f of x for all x very close to c. So let's take a look at how that's satisfied around x equals r. So it's true that the function is defined around r. So for any x value, a little bit to the left, a little bit to the right of r, the function is defined. And secondly, f of r is pretty big. F of r is that highest point there. And if I take x a little bit less than r or x a little bit more than r, I'll get function values that are a little bit less. In this picture, f is defined around p, but f is not defined around a. In the graph, f has a local min at x equals q, because f is defined around q and because, how would you complete the rest of this sentence? F of q is less than or equal to f of x for all x near or very close to q. Critical points are essentially the interesting points in a graph. Those are the x values where something interesting happens. So an x value, so first of all, point. Sometimes when I think of point, I think of something in 2 dimensions that has an x value and an x coordinate and a y coordinate. That's not the case here. In this case, when we talk about a critical point, we're always talking about an x value. All right. So an x value, c, is called a critical point of a function f if f is defined at and around c, and if either the derivative at c is 0 or the derivative at c does not exist. So in the picture, we can see several points where the derivative is 0. These are these nice smooth points that have horizontal tangents. The derivative is 0. Also at this terrace point, the derivative is 0. And here's a place where the derivative doesn't exist, a cusp point. There's no uniquely defined tangent line there. So in the picture, my critical points are going to be those x values where those things occur. So P, Q, R, S, and T. Here's our theorem. If my function f has a local min or max at c, then c is a critical point. All right. If it's a local min or max, then it's a critical point. Is the converse of the above theorem true? In other words, if c is a critical point, must f have a local max or min at c? And you answer this question with no. And here's the reason why. There's our counterexample right there at t. So t is a critical point, but at t it's neither a local min nor local max. We've been focused on graphically understanding maxes, mins, and critical points. Let's turn our attention to symbolic calculation. What if this function f of x is given to us symbolically? F of x equals x to the 4 minus 2x cubed, and we want to find the critical points of this function. What do? So first of all, let's find the derivative. I need to do a couple things. First of all, I need to solve where is f prime of x equal to 0. F prime of x equals 0, so 4x cubed minus 6x squared equals 0. Looks like I can factor out at 2x squared, and I'm left with 2x minus 3 equals 0. And so solving, let's see, looks like either x equals 0 or my 2x minus 3 equals 0, minus 3, which means in this second case x equals 3 halves. So x equals 0 or x equals 3 halves. That's just the first step. I still have more to do. I don't know for sure that those are my critical points yet. The next thing I have to do is solve. Where does f prime of x not exist? I'll just say solve f prime of x dne does not exist. If I go back a slide, can I do that? Here it is. Remember, these two things, to be a critical point, either the derivative is 0 or the derivative doesn't exist, so I have to figure that out also. All right, going back. But in this case, when I consider my derivative, does that ever not exist anywhere? No, it always exists. So I'll just write f prime of x exists for all x. So nothing new to consider there. The last thing I need to consider is my function actually defined at that point? Can I, and not just at, but around. So is f defined around x equals 0 and x equals 3/2. And so I go back to my original function and I say, what would happen if I plugged in 0 in there, or plugged in 3/2 in there? Is my function defined around those things? And the answer is yes. My original function is just a nice polynomial, nothing strange going on there. Okay, I've satisfied all the questions I need to know to determine if these are critical points, and so there we have it. I found my 2 critical points. They are exactly x equals 0 and x equals 3/2. All right, another example. Let's find the critical points of the function f of x equals x minus 5 to the 1/3 plus 4. I'll go like before. Let's find the derivative, f prime of x equals 1/3 x minus 5 to the negative 2/3. Oh, chain rule, I need to take the derivative of the inside now and multiply, but the derivative of x minus 5 is just 1. And then finally, I'll take the derivative of 4, and that's 0. Let me clean that up a little bit. So the first thing I need to figure out is, let's solve f prime of x equals 0. But look, my f prime is a fraction with 1 in the numerator. A fraction is equal to 0 exactly when the numerator is equal to 0. 1 is never equal to 0. So I don't have any values of x that are going to make f prime of x equal to 0. So I guess no solutions. All right, let's turn my attention to the second thing I need to figure out. Let's solve for when my derivative does not exist. Now my derivative is a fraction, and when does a fraction not exist? The fraction doesn't exist when the denominator is 0. So to solve for when my derivative doesn't exist, let's solve 3 times x minus 5 raised to the 2/3 equals 0. I'll divide both sides by 3. X minus 5 to the 2/3 equals 0. I will raise both sides to the 3/2 power, which gives me x minus 5 equals 0, and I will add 5 to both sides. X equals 5. So it looks like 5 is our candidate for a critical point. One last thing I need to check is my original function, is f defined around 5. So I go all the way back up to my original function, and I say, can I actually plug in 5? Yes, I can. If I plug in 5, the answer is 4. And if I put in a number a little bit less than 5, a little bit bigger than 5, is the function still defined? Yes, it's all good. So, yes, check. So, it turns out my only critical point is that x equals 5. There we have it. All right, our fourth point, absolute extrema on a closed interval. We'll bring together the idea of absolute max and min and the critical points. To find the absolute max and min of a function f on a closed interval from a to b, here's what we do. A, find all the critical points of the function in the interval. B, evaluate f at all the critical points and at the endpoints. C, identify the largest and smallest values. Here's the big idea. If I have a and b, and I have some function, and I'm really only interested in what is that function doing on the closed interval between a and b. My attention is all the way on just that little segment of the function. So where can the absolute max and min occur? Well, they can occur at critical points, so something like that, or they can occur at endpoints. So I find the critical points, I find the endpoints, I plug in those points into the function, and I find the highest and lowest values. We'll go through 3 examples. The 3 examples you'll see there, and we'll just do them one at a time. Find the absolute max and min of f of x equals x to the 4 minus 2x cubed on the interval from -2 to 2. Now, this was a function we looked at before where we found the critical points. The critical points were x equals 0 and x equals 3/2. So now, all we really need to do is, let's plug in the critical points into my function, f of 0, f of 3/2, and I'll plug in the endpoints into my function, f of -2, f of +2. So I took these things and I plugged them into my calculator. So look for the highest value, looks like 32. Look for the lowest value, looks like -1.69. And so those are going to be the absolute max and absolute min of the function on the closed interval from -2 to 2. The very highest value that it attains is 32. And the very lowest value that this function attains on that interval is a -1.69. And that's it. All right, next example. Find the absolute max and min of the function f of x equals x minus 5 to the 1/3 plus 4 on the closed interval from 4 to 13. Again, this was an example we looked at earlier for the critical points, and we found there was one critical point, x equals 5. So I need to figure out f of 5, and I will also figure out f of 4, and I will figure out f of 13. The absolute max that this function attains on the interval from 4 to 13 is 6. The absolute min that this function attains on the interval from 4 to 13 is 3. Last example. A little more challenging, and I haven't found the critical points on this one, so I need to go through the whole process. Find the absolute max and min of the function f of x equals x to the 4 times e to the -2x on the interval from -1 to 1. First, I need to find the critical points. Find critical points. So I'll find my derivative, f prime of x, is up, and I need a product rule. So 4x cubed e to the -2x plus x to the 4 times, now I need a chain rule. What is the derivative of e to the -2x? The derivative of -2x is -2, so I'll bring the -2 down, e to -2x. Let's clean this up a little bit. Next step. Let's figure out where is the derivative equal to 0 and where does the derivative not exist. So solve f prime of x equals 0. It looks like x equals 0 is a candidate. What about this factor e to the -2x? E to the x is never 0. Right? E to the x is never 0, so e raised to any power is not going to be 0. So this factor e to the -2x can never be 0. So I'll move my attention to my final factor on the right, 2 minus x, in which case x equals 2. So there are two values of x that can make this derivative 0. X equals 0 and x equals 2. The next thing I need to ask is, let's solve for f prime of x does not exist. And we can see here that any value of x I plug into my derivative will exist. The function is defined there, so nothing to worry about there. And the last thing I need to address is what about my original function f? Is f defined around x equals 0 and x equals 2? So I'll go back to my original function, and yes, it is. It's a product of two continuous functions, so f of x itself is continuous. It's defined everywhere. So I have my two critical points. My two critical points are definitely x equals 0 and x equals 2. Now, we turn our attention to the closed interval from -1 to 1. What is the absolute max and absolute min of this function on the closed interval from -1 to +1? I'll erase all the markings and address that. So I need to figure out f at my critical points, 0, f of 2, and at the endpoints, f of -1, f of +1. Oh, but actually, you know what? This f of 2, I don't even need to consider that at all. All I really care about are the critical points that lie within the closed interval. So, nope, take it out of consideration. We don't need it. So what about f of 0? So f of 0 is 0. F of -1 is e squared. And f of 1 is, in fact, e to the -2. Let's see, e squared is approximately, I did this in my calculator, 7.39, and e to the -2 is approximately 0.14. So finally, after all that work, we have it. What is the minimum value? It looks like 0 is the minimum value that the function attains. And what is the maximum value? E squared, or about 7.39. All right. There we have gone through examples of finding an absolute max, absolute min on a closed interval. We've looked at local maxes and mins, and we've thought about critical points. We have all the ingredients we need to do some nice analysis on functions and finding their maxes and mins. Go to it.